Okay, we are ready to start this afternoon session. And the first speaker is Balogh from Urbana-Champaign in Szeged. He will tell us about the structure of typical Kr+1-free graphs.
Thanks for the possibility to give a talk for this quarterly conference. So I modified the subject of the talk a little bit. So in the first 30 minutes I will talk about surrounding area, which is corresponding to the family. First I started the well-known high school puzzle. So that how many integers you can choose from the first and integers without creating a solution of the equation expressed by C. So one observation is that if you take 3 as integers, then just take 2, then the sum of 2 as integers is even, so the set of arts is always something. And so this gives an answer n hat, that is the construction. And other bound is if you take the n hat largest integers, then this set is again something, because if you just sum up the smallest one, so if you sum up the smallest one, then it's larger than the largest integer, right? Here I got so the question of Cameron-Erdős was that how many subsets of the integers exist, which is something, and they conjecture that it should be big O times 2 to the n hat, and this construction shows that up to the constant factor this conjecture is best possible. And this conjecture was solved by Green and Schacht positively. So one can ask, okay, if the conjecture is solved, then what else can be done? And with Conlon, Gowers, and Samotij, we prove the refinement of this result. So the refinement is that we were asking the number of some free subsets of the integers of the fixed size n, and we prove that it is roughly, so roughly like n choose 2 times n. This factor is naturally value the size of the largest free subset has size n half, and there is a correction function is put to the Cn over n, which has a very interesting property. If m is large and this factor is constant, but if m is getting smaller and smaller, then this function is suddenly getting bigger and bigger. For example, if you substitute the values of all m and sum it up, then this proves the Cameron-Erdős conjecture, but it's somewhat weaker result than Green and Schacht, because they actually determine the constant in front of to the other. So the idea of the proof is the following, or the sketch of the proof. First we use the upper bound on the number of independent sets in 3 uniform hypergraphs, and we use some robust stability result of left projection and Green and Schacht. So the robust stability result of this type is that if you have a large sum free set, in size close to be n-half, then there are two cases. Either it is close to the set of odd integers or close to the set of large integers, or the other possibility that this set contains many sums. And the other part. So the set of integers for Turan is very not symmetric, because the number 1 and the number n is behaving very differently. It's a more natural surrounding. It is considering Abelian groups. So here I just mentioned the simplest possible case, and G is an Abelian group with that the number of elements has a prime divisor Q, which is equal to 2 modulo 3, and we can fix the smallest such prime. And denote mu G the density of the largest sample subset of G. Then a whole theorem of G and he agrees that the maximum density of sample subset is 1/3 plus 1/3 cube. If you look just the simplest example for the Abelian group, the Z2n, then in the Z2n, the set of odds is sum free, Q is equal to 2, and this sum is equal to 1/2. And the structure, describing almost all sum free sets for such groups where Q is equal to 2 was done by Balogh and Schacht. So they prove that if the order of a group is even, then almost all sum free subsets lie in the complement of the subgroup of index 2. So you can just think of Z2 and the evens are a subgroup of index 2, the complement is the odds, and this says that for such groups almost all subsets are subsets of the points, and like Conlon-Gowers this was true for other groups as well. So here we proved also refinement of this theorem. So we proved that if M is sufficiently large, then almost all sum free subset of G of size M is contained in the maximum sum free subset of the group G. The natural control bound is like root n, because if you have a random root n chosen elements of the group, then it's unlikely that sum is appearing anywhere. So something about the proof technique. So just showing some literature that there was a paper of Alon where the title said that independent sets in regular graphs and sum free subsets of Abelian groups. Schacht had two papers appearing about the same time. One is about independent set in expanders, the other is about counting sum free sets in Abelian groups. So, not surprisingly, one of our key tools is a lemma which counts or gives an upper bound on the number of independent sets of size n in an n-vertex irregular graph. So if lambda g denotes the eigenvalue of G, and lambda satisfies that lambda G is at least minus lambda. Then the number of independent sets of size M is at most lambda over T plus lambda plus epsilon n choose M. So just assume that G is a bipart like that, and this lambda G is minus D. So here the lambda plus D plus lambda will be 1/2. So it's not surprisingly we get that 1/2 plus epsilon n choose M in this special case. So let's try to explain a little bit how the independent sets in graphs corresponding to some three subsets of groups. So let G be a group, and S be some three subset. Then we define G as star the following way. The vertex set of the graph should be G minus S, and the edge set should be that we connect two elements of the group if their difference is in S. So now assume that we want to count number of sum free sets. So assume that I is a sum free set. Then we choose a set S of size epsilon m. So S is a small set. Then we should observe that I minus S is an independent set in this graph. Otherwise, there would be a sum in I. So if we count the number of choices for I, then first we have the number of choices for S, which is small because S is a small set, and the number of independent sets in this graph that we define. And this way we can get a reasonably good estimate of the number of sum-free subsets. So let's see different problem. Consider arithmetic progression-free subsets of integers. So the well-known external result of Szemerédi that any positive density subset of the integers contains an arithmetic progression of type A if n is sufficiently large. So we need a robust version of this theorem, which was actually known earlier than Szemerédi's result. So the robust result said that assuming that Szemerédi's theorem is true, then every linear side subset of n contains not only one arithmetic progression but contains corresponding arithmetic progressions. This can be proved by an averaging argument. So just to summarize, this robust statement says that if you have a subset of integers of size at least epsilon n, then it contains very many arithmetic progressions. So to count arithmetic progression-free structures, we can do the following way, that we use a transference principle that I will talk about later, so that for every AB-free subset of integers, we should find a subset of the integers which is still not very large, that was some epsilon n elements, and that there are not so many choices for I. And using this idea with Morris and Samotij and independently Schacht and Thomas to do the following result, that if M is sufficiently large, where this boundary is practically shared, the number of subsets of the integers up to n of size n without the arithmetic progression of n k is at most delta choose m, where you can choose delta to be an arbitrary small constant. So one can ask that, okay, why this theorem is interesting? So I try to place this into the history. So originally, Erdös and Turan asked the question that what Szemerédi solved, that what is the size of largest size of the A50 set, and this can be formulated this way, but I already said this, or this theorem or this conjecture was proved finally by Szemerédi, and we defined the following concept, the so-called delta k Szemerédi property of subset of integers. So we say that A is delta k Szemerédi if every B subset of A having size at least delta times A as an arithmetic progression of type K. So using this definition, Szemerédi proved that the set of integers on up to n has the delta k Szemerédi property. So it's a natural question that what other sets have this Szemerédi property. And here I should mention probably a whole class conjecture of Erdös, which states that if there is an infinite subset of the integers whose reciprocal sum is equal to infinity, then this set contains a logarithmic progression. And the special case was solved, but here they actually proved a little bit more. So Green and Tau proved that the set of primes contains long arithmetic progression, but they also proved that the set of primes has this delta k Szemerédi property. And one can ask that what's happening for a random set. So the random subset of set should be that for each element of the set we take independently a bias point where the probability of success is P, so we create a P random subset of P. And the question is that for what P has this random subset of the integer, we have the property delta k Szemerédi. And the Green and Tau pointed out that their methods prove that if P is larger than n to the minus ck, where ck is a small constant, then the random integers have the delta k Szemerédi property. Here I should point out that this question was phrased by Kuhayaka, Buchak and within 96, and they actually settled the case when k is equal to 3, determining best possible value for So there was a breakthrough like 4 years ago, or now 5 years ago. Conlon-Gowers and Schacht proved some general transference theorems. So we proved that if there is some external result, so like in our case the Szemerédi theorem, and there is some supersaturation result, so like in our case this Corollaries generalization, then the random analogue of the result one. So, for example, they settle this random Szemerédi question. So they prove that if P is sufficiently large and they have the best possible value. Then with high probability, every linear size subset of random subset contains a Kr+1-free. So with other words, they found the threshold for the delta Kr+1-free property. So this is the point where our counting is fitting into the theory. So we counted the number of Kr+1-free sets of size m. So this implies easily the random analogue of Szemerédi's theorem, and it is just implying the first moment method. So simply if you have a set which is not it doesn't have a delta Szemerédi property, then it means that it contains a large subset which has no Kr+1-free progression, and then we just bounding the probability that the random subset contains such a set, and by the first moment method we prove that the probability of this is exponentially low, and we use this complete. So now I turn to the topic that I promised in my outside, the Turan problem. So the Turan theorem is the following, or Turan question, that if you have a graph H, then Ex and A is the maximum number of edges in an m-vertex H graph, and if H is the complete graph of A vertices with KK, then Turan's theorem states that this maximum is achieved the way that you partition the vertices into K-1 sets, and you put all possible edges between the graphs. And it doesn't contain KK, so it's Turan's theorem. And the question that we are more interested in the counting version, so that how many KK-free graphs on n vertices are there, and observing that if you have a KK-free graph, then every subgraph is KK-free, so we find at least 2 to the external number of KK-free graphs on n vertices, and it was proved by Erdös-Kleitman-Rothschild in 76. This bound is close to the best possible. This is a slightly correct version of the theorem. So here we are looking Turan's theorem in the way that you consider the complete graph, and you are wondering that what is the largest subgraph which does not contain KK. So the Turan's theorem could be stated the way that if you have the complete graph, it has a subgraph which has at least as many edges that this number from Turan's theorem times the number of edges of the complete graph, then G contains KK. So instead of Kn, we could write arbitrary graph R. So we might add that what other graph R has this Turan property that take any subgraph, and the proportion of the edges of G is as much as we see. Just we multiply instead of the edges of R, instead of the number of edges of E, and then G contains KK. It's clear that not every graph has this property. For example, if R doesn't contain KK, then we can keep all of the edges. Notation-wise, we can use the notation XRH, the largest number of edges in an H2 subgraph. So it's an easy lower bound that if you take take a max gate cut, then you can find a large KK-free subgraph of any graph. So the question is that typically this is best possible for other graphs. So if we say that typical, then we usually mean that we are talking about random graphs. So let G and P the standard random graph, so the probability of merge is P independent of the others. So we are asking that for which P the following is true that the largest KK-free subgraph of G and P has almost as many edges as the number of the edges of the random graph times this equals the Turan's theorem. And that is usually called as the random analogue of Turan's theorem. So here again we need some lower bound on P, because if P is too small, that the number of copies of the KK is less than the number of edges, or much less than the number of edges, and then this definitely does not hold. And the conjecture of Balogh, which I can reveal, was that the random analogue holds when P is sufficiently large, and this value was our best possible. And there were lots of work on this topic, and somehow when K gets larger, then the length of the paper gets doubled. So somehow it was like if this transference theorem came otherwise it would not be in trouble. So the transference theorems of Conlon-Gowers and Schacht would be applied for this case as well. So here the external result is the Turan's theorem, so that if the number of edges is more than the external number, then there is a KK. And the Erdös-Kleitman-Rothschild separated version of the Turan's theorem is that if you add some deltas per extra edges, then you create suddenly some epsilon edges in the KK, so suddenly you have many copies of KK. And then these two statements are enough to obtain the random analogue. So what we were interested in was counting values. So the Erdös-Kleitman-Rothschild result and roughly correct way estimated the number of hypergraphs, estimated the number of KK-free graphs. So what we looked at, we fixed m the number of edges. So we are interested in the number of KK-free graphs, exactly m edges. So one can ask that when is it true that the number of KK-free graphs is and edges is at most trivial, or the upper bound that one would expect that you have the external number plus epsilon square, choose so the idea of such a proof or such a statement would be that it would be easy if almost all KK-free graph was a subgraph of one graph with that many edges, because then just using this counting result we prove the theorem. But it's clearly not true. One can construct many KK-free graphs which are very far from having K minus 1 quantity. But it is sufficient that instead of saying that one single graph, we prove that every KK-free graph is a subgraph of a small number of graphs having that many edges. And small is can be as large as n squared to n. You can see that it's a big number, but not compared to this number. And with Morris and Samotij, we proved that such statements are true. And we actually proved the sharp characterization for Kr+1-free graphs. We had an example of it's a one-cat. So this is just to show that life is not simple. This delta is a constant depending on R, and MR is the this constant times the n power times some log raised to some other power. So rather better to look simple state version of the result. So we determine the function mn, which was represented in the previous page, such that almost every Kr+1-free graph on n vertices with m edges where m is more than mn are the alpha type. And this mn is best possible. This result was known for the case of triangle by Kr+1 and so some ideas about the the transference theorem proved in step 1 that almost all Kr+1-free graphs with M edges can be made R-partite by removing at most the 2M edges, so that most of the Kr+1-free graphs are already almost R-partite. And the next statement is kind of showing the bottleneck. One case that we have to consider carefully is coming from why the bound on M is sharp. So assume that you want to construct many, I just have a triangle case, you want to construct many Kr+3 graphs, then how would you do it? You just put one edge to a class, so you partition it into two parts, vertices and half vertices. Just to put one edge into one part, hoping that they don't have a common neighbor. And if M is not large, then it's likely that we can always find such pair of vertices where such an edge can be placed. And the proof is fighting with two cases accordingly. So one case is when there are vertices which is in an optimal partition. The optimal partition is a partition which is a max cut. So one case is when there are vertices who has large degrees in its own class, and if I oversimplify like 10 pages of proof, then the counting is that if you have such a vertex with high in degree, then it has many neighbors in the other class. So between them it's likely to have an edge, so we are likely to create a triangle. And other case is similar when you have just one edge, but it could be that you have more edges, and that you don't have high degree vertex. But the rules of handling these cases are quite long and technical, and in particular we use the Jansson's inequality many times. So in the remaining time, instead of going to the technicality of this, I try to state the transference theorem and how to apply the transference theorem to get the first step of the proof. So just show the outlaws. So this is contact, this is row, this is here, this is contact. So the transference theorem is following. So assume that we have an R-uniform hypergraph. I H was independent sets in H. Then the aim is that we want to cover the independent sets with a very small number of sparse sets. So for this we define the non-sparse set, the dense sets. So F with a subset of vertices which are dense. Then we prove the existence of some M0. We define a family of so-called labels, and prove the existence of labeling functions. The labeling function labels the independent sets with a label, and a function from the labels to the sparse sets, such as for every independent set, the label contained in the independent set, and the rest of the independent set is contained in the sparse set. So this is the main transference theorem. Similar result was proved by Substituent Thomas, and on a figure I think I can explain the statement a little bit better. So let this be the power set of the vertex set of the hypergraph. So here we have the collection of subsets of vertices which are dense. The independent sets are somewhere here, and in the very bottom we have the labeling sets. So the sparse sets are somewhat above the independent sets and below the dense sets. So if we have an independent set, then for the independent set we have a label set. For the label set we have a sparse set, and this has the property that they contain together the independent set. And this has many corollaries. For example, to the Sparse analogue Erdös-Kleitman-Rothschild theorem, then prove this theorem that almost for every Kr+1-free Darcy damages are almost K-1 So the Kr conjecture I don't state it, and the random analogues Turan and Szemerédi theorem. So like how to apply to get the discounting version for the arithmetic progression. So the important thing is that we have to define a hypergraph. So the vertex set of the hypergraph is the set of integers 1 up to n, and the hyperedges are the arithmetic progressions of like k, and the independent sets in this hypergraph are subsets of integers which doesn't contain arithmetic progression. So if you characterize the independent set, then we characterize the k arithmetic progression subsets. For the Turan problem, the vertex set of the hypergraph will be the edge set of the voltage graph, and the edge set of the hypergraph will be the edge sets of the copies of the k's. So here we define the k choose 2 uniform hypergraph, and the independent sets in this hypergraph will be graphs which does not contain k as subgraph. And this can be applied actually with the sum-free sets example. Just now the vertex sets are the group elements, and the three edges are the equals where x plus y is equal to 3 has solution. Here we define that all these levels are different. The sketch of proof, but describe how to use it. Let's say in this AR+1 example. so the vertex set is the edge set of the complete graph. The edge set are the copies of the Kr+1s. So independent set is the Kr+1 free graph. So we get some small t from our theorem and a collection of t graphs such that any Kr+1 free graph can find a GI that is the subset of GI. I would say here that you can find one graph which has this property, the complete graph. So, but we have additional criteria that each of the GI has just equal n to the r+1 Kr+1s. And super saturation plus stability theorems implies that each of these GI satisfies one of the following properties. That either GI is almost R-quartile or the number of edges is significantly less than the maximum number. And now we can just count the number of Kr+1 free graphs that for any graph is either we are in that case or in this case. If we are in this case, then most of the subgraphs will be almost R-quartile, and if we are in this case, then we don't generate too many subgraphs because of this minus. But the only thing that I could say is the sketch of the covariance requires that this file is used. Thank you.
Questions?
Can you say something about the constants? Is it possible to make it split apart, obtain the best constant, for example, random?
Which constant?
For example, for probability threshold, the order just constant in your first one, and you are finding this independent sets of size n. Any other type of
In general, it's hard to get type about
maybe just some more some bounds.
the bounds are not really. For some special case, there are some sharp results like Erdös, but it's very specific statement. So in general, the dependence of the constant.
Any other? So actually for lines, if you choose a random subset of the lines, it's also okay.
I think yes.
Because in general you can combine those, so suppose for the Turan thing they don't start with complete graphs and they start with a graph with meaning the point is now in. So it's non-written such graphs